So now let's discuss about padding. What is padding? Suppose consider the sequence 1, 2, 3, 4 and followed by 10 zeros. Why we are adding these 10 zeros? Because we are just padding to have maximum length. So when we are adding zeros, our model will end up training these false values or these zero values mostly. So this will affect our training accuracy or training loss and finally accuracy. So we need to find a way in order our model not to train on these values. So that is called masking. Basically we have two types of masking. One is padding mask, which we are doing here. So first let's discuss about padding mask and later on we'll be discussing about look ahead mask. So in padding mask what we are simply doing is we are having a sequence 1 2 3 4 0 0 0. So first thing we would be converting it into an embedding layer. Okay, we are converting these into an embedding layer. So we are not interested with these zeros. So what we do, we will mask these zeros. So what actually is masking is we are not considering these query key and value vectors in calculation of this. Like we are doing query q and q transpose k. So we are not considering the values from these masks. So when you are doing multi-head attention and whenever you send a parameter as mask, so the multi-head function will implement in such a way that the masked values are not being considered for calculation of scale dot product. This is about masking. So how can we do this? Let us go to the example. So here we have taken padding masks and we have created a layer from Keras so that we can use it as a Keras layer. And next we are calling mask. And basically whenever you are inheriting Keras layer, it's not necessary that you need to call the function specifically. So whenever you just create an instance of the object, it will automatically call the function. So no need to write padding mask dot call. It basically implements it. Okay. So what is the argument for this? We are sending input and we need to see whether it is zero or not. So let us rewrite this code here. Let me copy paste it and we are see here we are typecasting it to float. That's it. So let me take the inputs as an array. Let me take it as ones. So let the shape be 1 comma 3 comma 3 and if I run this, it is taking some time. Okay, let us revisit it again. And next thing is we are having a look ahead mask. What is look ahead mask? See, while we are training, let me clear all the stuff. And while we are training the data, like suppose we have the input sequence 1 3 8 5 0 0 0 0. This is our encoder block. This is our decoder block. So what we are doing, suppose the decoded sentence or the converted sentence was 4, 18, 16, 30 followed by zeros. So this is the, let us assume this is French translation, this is English translation, 4, 18, 60, 30 followed by zeros. So here we are, what we are doing, we are calculating query key and value pairs and we are having positional encodings and all those stuff. See, we are here we are able to access the next time steps query key and value pair. Suppose you are calculating embedding vector for 1, you are having access to 3, 8, 5, 0, 0, 0. So while training, you are able to access these values. So, but it's cheating, right? So what we are doing is we are creating mask which is called look ahead mask. So what look ahead mask does is, so initially we have only one sentence. Suppose our converted I am a student. Let us assume this is the English sentence. Let us assume the converted sentence. I am writing it in Telugu because I don't know French. Nenu oka vidyarthi. Okay. So what we are doing, we are having access to all this sentence for encoder. But for decoder, we initially have start of sentence. So we are not having access to all this. So what we do, we mask these values 0 0 0. Okay, and when it predicts nano, so you are having access to nano, you don't have access to these two, so you are keep hitting 0, and the same thing follows. So it's like 1 0 0 0 1 1 0 0 1 1 1 0 1 1 1 1. So it's simply a lower triangular matrix which we get in creating a look ahead mask. So let us implement that here. So we are having a lower triangular matrix. Let me copy this and paste it over here. Let me write maximum sequence length to be 4, and if I execute the statement, say I got a lower triangular matrix of this shape. So what if I write here 5 or 10? Same thing happens. See, this is the lower limit, this is the lower limit, and this is the upper limit. You can also go through the documentation of this bandpart function so that you will be getting a clear understanding of how we created a lower triangular matrix using TensorFlow. So this is all the stuff which we need before getting started with the input layer encoder. So what we have created a positional encoding, we have created padding mask, and we have also created look ahead mask. Now it's time to create an encoder. So initially what we are having, so this is our block diagram. So initially we are having inputs. We are having inputs. We are adding positional encodings, and we are giving it to our input layer encoder. Sorry, not exactly. Let me tell it once again. So initially you are having sequences. You are representing them in the form of embedding. You are adding positional encodings. After adding positional encodings, you are having all this stuff like mask and every other thing. So let me show you in the code. So initially we are creating input layer encoder class, and we are inheriting layer from Keras. And what we are taking, see, we need to have the access for maximum sequence length because we are creating positional encoding inside input layer encoder. So what does this positional encoding takes maximum sequence length and embedding size. So we need to have access for these two. So maximum sequence length and embedding size. And also we should have the access for vocab size. Why we need to have the access for vocab size? Because we are creating an embedding layer. So we need to have access for vocab size. So that's what we have done. We have created a padding mask. We have created an embedding. So basically in embedding, we'll be having the vocab size as first argument, and we need to have embedding size, and the input length is the maximum sequence length. These two are optional. So even if you do not give this, this will work out. So you need to uh, first give vocabulary size as well as embedding size. So we have created an embedding. We have also created positional encoding. So we have stored all this inside the class, and whenever we create input layer encoder and we call this, we'll be executing these statements. So initially what we do, sorry, we are having inputs. We are we are applying the padding mask. So initially let us assume our inputs are 8 16 00 00. So whatever masking does, it will give this output. So this is the first step. Second step, we are doing embedding. So what we are doing, we are converting. So we will first write this. So we'll be having 8 16, and these all are masked things. Now we'll be applying embeddings. So this will be converted into embedding. Okay. This will also be converted into embedding, but we do not consider because we send it as mask. We'll be sending mask. So whenever the multi-head attention looks over this mask, it will not consider these embeddings. Okay. So we'll be having we'll be having embeddings. So we are creating embedding, then we are adding positional embedding. Sorry, positional encoding. So we are adding positional encoding to this. Okay. After adding positional encoding, we are just returning the embedding as well as mask. So why we are returning the mask? So we are returning the value of embedding to the next encoder, to the encoders above this. So this is basically our structure. We'll be having encoder, we'll be having encoder block, we'll be having encoder block, we'll be having encoder block. So we'll repeat this n number of times. So it is a hyperparameter. You can choose anything, but in the base paper they have chosen 6. In this implementation I have done with 2 as well as 6, and I found that 6 has better results. Okay, let us go through it afterwards. So what we are doing, we are sending our embeddings as well as mask. So initially let us assume this is our maximum sequence length. We have embeddings like this. As I already told you, all the encoder layers will have the same input. So the encoder layer here will also have these inputs. So it requires something called mask, because it need to mask all this stuff. So that's why we are sending mask. So we are sending embedding as well as mask. So this is what we are returning. And whenever we create encoder layer, we'll be understanding. Let me execute the statement. Okay. Let me create, okay, I have already implemented the code. See, initially I'm initializing the input layer encoder. Then I have taken an array 67814. Then I'm adding the positional encodings. So this is the step. So if I want to look at the positional encoding, just I'm accessing the object from class. This you can just play with on. Okay. So see, initially this was my shape, so I got 1 comma 5 comma 10. So why I got 1 comma 5 comma 10? Because 5 is the maximum sequence length and 10 is the embedding size. So that's why I got this shape. Now let us understand input layer decoder. So let me first tell you about encoders, then I'll be telling you about decoders. So initially we have implemented input layer encoder. Now we'll be implementing encoder layer. So what encoder layer will do? First thing, as I already told, you need to remember that we are calculating query key and value pairs, and we are doing scale dot product, and we are applying softmax to that. So this was our formula, root dk times query key, and this is the value. This was the formula. So you can simply do it in Keras by using multi-head attention of query key and value pairs, and an optional mask. You can send it or not. If you send the mask, it will consider it. If you are not sending the mask, it will not consider. Okay, so you are sending. Okay, initially we need to create an instance for multi-head attention. So the inputs are number of heads. Like you want, if you want 3 heads, you'll be writing heads is equals to 3. If you are having 8, if you want 8, you can use 8. In the base paper, I think they have used 8. So it's a hyperparameter again. And key dimension, we need to see here we are sending a very key and value pair of some dimension, right? Like in the base paper, they have used 512, I guess. So you need to send the embedding size. So that is key dimension and dropout. This is a kind of regularization. Okay. Next, we are creating a dropout regularization here also, and we are creating a feed forward network. So I have created a 2-layer feed forward network. First thing is having embedding size dimensions, and the second thing is, okay, I think this is wrong. I need to create 2 layers. It works fine if you are just using 1 layer also, but let me create 2 layers. So the input is dense num. Oh, where is it? Yeah, dense num. So what we are doing, we are creating activation. What actually we are doing is we are creating a feed forward network having dense num and embedding size. So basically I'll be showing you, this is the feed forward network. This is dense num. So we are having these many number of neurons here, and we are having embedding size number of neurons here. As I already told you why we are having embedding size, because our encoder layers, which will be processing further should have the same input size as it gets. See here we are giving input size as embedding size. That's why we are ending up this feed forward network with embedding size. And we are also adding a dropout layer, and we are creating normalization, layer normalization, and we are having two normalizations. As I told you in the block diagram, we'll be having two normalizations. So simply normalization is we are actually taking up residual connections and we are just normalizing the data. So we can directly implement it using Keras layer normalization. Okay, that's for initialization. Let me show you what we do when we call the function. Okay, when we call the layer. Okay, so initially we are calculating multi-head attention. So the inputs are inputs, inputs, inputs. So we are giving the same inputs. See, we are giving same number, like we are giving the same x value. Suppose this is x1, this is x2, x3. So we'll be giving the same x values. It will calculate query key and value based on different weights. So it will be taking different weights. It will initialize these three weights differently so that it will calculate query key and value pairs. So our inputs will be same inputs, inputs, and inputs. We are giving a mask which we get from input layer encoder, and we are taking layer normalization. Then we are also creating a feed forward network. Then we are adding dense, and we are creating other feed forward network. So what we are doing is simply we are calculating multi-head attention. Then we are adding inputs and this output. Then we are passing it through feed forward network. And if you are familiar with the diagram, you can understand this code. So this is about encoder layer. Now we need to create an encoder. So we have done with encoder layer. Let me delete this. So we have created just one layer of encoder. But what exactly we do? We need a full encoder. So initially here we'll be having input layer encoder, and we are repeating encoder blocks n number of times, and we need to get an output which is embedding. So what our layer encoder layer should return? An embedding. So this is what is embedding. Okay. Next we are creating an encoder. So this is also a layer element. So we are inheriting Keras layers, and we'll be having maximum positional, maximum sequence length, embedding size, vocab size, and number of heads, number of dens, and number of encoders. See, this is, as I already told you, number of encoders is the hyperparameter. So based on your requirement, you can change this value. So initially we are creating input layer encoder, then we are iterating encoder layer n number of times. So if you want 10 encoders, we are creating a list of 10 encoders. We are initializing encoders, and other thing to remember is we are not using the same encoder weights. See here we have the same encoder, encoder 1. Suppose this is encoder 2. These two encoders will be having different weights. So we are creating an encoder layer n number of times. Okay, and we are taking the number of encoders as a global variable inside this class. Then what we are doing, we are initially calling the input layer. We'll be getting embedding as well as mask. What we are doing, we are taking skip as embedding, because we are adding or normalizing the data. We need a skip connection. As if you see the diagram, you can understand we are doing residual connections. That's why we have taken skip, and we are iterating through each layer, and through each layer what we are doing, we are sending embedding as well as mask, and this training is a parameter which will be used for dropout. So during training we'll be using dropout, but when we are testing we do not need a dropout layer. Okay, just dropout layer is to regularize the data. We are using dropout layer for regularization. It is not necessary at the time of test. So this is a boolean. If this is true, it will implement the dropout layer. If it is false, it will not implement the dropout layer. Okay, and next what we are doing, we are doing adding a normalization, which we have done here. Then we are assigning skip to embedding, then we are returning embedding as well as mask. This is about encoder layer. Now we are implementing decoder layer. So initially we need to implement input layer decoder. So what we are doing, we are taking the same padding, we are taking embedding as we have taken in the input layer encoder, we are taking positional encodings, and the other thing which we are doing is we are just taking a look ahead marks extra. So we are taking a look ahead mask. Initially we are creating a padding mask. So what does padding mask do? It will just put whenever there is 0, so it will consider based on that. And we are creating embeddings. We are also adding positional embedding. So what we are doing, we are having, suppose this is a mask 1 2 3 0 0 0 0. So whatever padding mask does, this will give this output. Now what we are doing is we are having a lookahead mask. Our lookahead mask look like this 0 0 0. So actually let us consider for five sequences: 1 1 1 0 0, 1 1 1 1 0, 1 1 1 1 1. So what we are doing, we are doing bitwise and for all this stuff. See, we are not interested in these values. So we need to remove all these values. So we need to set all these values to 0. So our lookahead mask look like this: 1 1 0 0 0, 1 1 1 0 0, 1 1 1 0 0, 1 1 1 0 0. So we are not interested in these padded values. That's why we have added this. So in order to achieve this, we can do just bitwise AND operation. So I have created a lookahead mask initially, then I have done bitwise and for a lookahead mask as well as padding mask, and then I have returned our embedding as well as lookahead mask. Why we are returning lookahead mask? Because we will be using in the further decoder layers. That's why I have returned embedding lookahead mask. Okay, now let us implement decoder layer. So if you had a proper understanding for encoder layer and encoder block, you'll be having a better understanding for decoder layer and decoder block. What we are doing, we are doing the same thing, but this time what we are doing is we are adding masked multi-head attention and other multi-head attention. As I already told you, masked multi-head attention is for decoder block, and multi-head attention will be taking inputs from encoder layer. So we are doing these two stuff, and all the other things remain same. As here we have two different attentions, that's why we are having three normalizations and two dropouts. If you are using only one multi-head attention, I mean in the encoder layer, that's why we got only two layer normalizations. Okay, now let us implement masked multi-head attention and multi-head attention. So we are, this is optional thing, you can remove all this also. Let me remove this, or let me keep it. Okay, so what we are doing, we are implementing masked multi-head attention. What are the inputs? Inputs and inputs. So these are the decoder inputs. Okay, we are implementing, we got masked multi-head attention output, then we are doing add-on normalization with inputs. And the second thing what we are doing is we are taking query from this value. We are taking query from decoder output, and we are taking outputs from encoder, and we are doing sorry, we are doing multi-head attention. So the two arguments are encoder output and encoder output. Based on the encoder output, we are calculating multi-head attention output. So let us assume this is MHA output 2, and we are adding and normalizing the data. We are passing it to feed forward network. We are doing dropout, and finally we get output. This is about decoder layer. This is same as encoder layer, but a slight difference. Let me run this, and this is implementation of decoder block. We are having maximum sequence length, embedding size, vocab size, heads num, dense nums, and number of decoders. So in the base paper they have used same number of encoders as well as decoder, but it's your wish, you can use different number of encoders and decoders. I have been trying with different numbers, but I found out that if you are using the same numbers, I got better results. And it's your choice of using number of decoders and number of encoders. Okay, so what we are doing, we are taking embedding and lookahead mask from input layer, and for each layer we are adding skip connection. This code is same as encoder layer. If you look at it, you will be understanding this. So we have created encoder and decoder layer. So what we need to do finally, so what we have implemented is, initially we have input layer encoder, we have encoders, we have encoders, we have encoders. So instead of all this stuff, what we have done is we have replaced everything inside encoder block. So if I implement the class encoder, all these things will be implemented. That's what we have done now. And if I write decoder, all this stuff will be implemented. So in transformer, so finally what we are doing, we are creating a model, right? So what we basically do in Keras, we'll be using sequential model, or we'll be using model keyword in order to create a model. But here we are creating a custom model, so that's why we use tf.keras.model. So it will create a model for us. So let us initialize all the arguments. We are creating an encoder block. So encoder is the code which we have done here. So all these arguments will be passing it over here. Okay, all these arguments will be passing over here, and we are creating a decoder block, and we are creating final feed forward network, then softmax. Why we have taken axis is equals to -1? Because we'll be having categorical cross entropy loss. So what we are doing is our output, suppose our sequence length is 10, our output will be 10 by vocabulary size. So what we are doing, we are getting output in the form of one hot representation, because we'll be having vocab size number of classes, right? So we need to predict the most probable one. So it is around the last axis. So axis is equals to -1 we have used. So we are taking the maximum out of it. Like we are just performing a softmax for the last layer. That's why we have taken axis is equals to -1. So initially we are having inputs. We are these inputs will be coming from this one. Like whenever I'm writing fit, so this is the input which I am giving. So we will be extracting input and output sentence. We are calculating the encoder output and encoder mask from encoder, decoder output from decoder, and finally we have implemented all the stuff. This is about transformer. Now before running this model, okay, let me create the instance of transformer. Let me run this. So I have created the instance of transformer model. I have taken maximum sequence length as 14 and this to be 13. Why I have taken 13? Because see, initially our input and output are 14 and 14 length. But in decoder, initially we will give one start of sentence, then we'll predict one output. Let it be O1. So we are giving O1 again, we are getting O2. We are giving O2 again, we are getting O3. So it goes on. If you want O14, we need to just give O13. If you want O13, we need to give only O12. So we are having one length. So we need to subtract one length because we are just giving from 0 to 13. We need to predict from 1 to 14. That's the basic maths here. So simply what we are doing, the maximum length to be 13. Okay, embedding size I have taken 300 and it's a hyperparameter again. And vocab size is, if I'm converting French sentence to English sentence, I'm taking vocab size 1 as French vocab size and vocab size 2 as English vocab size. Then heads num. So it's your hyperparameter, you can give anything. If you want to just follow base paper, you can give it 8 I guess. And dense num to be 512 I guess, and number of encoder decoder is 6. Let me run this. And before summarizing the model, before just directly fitting the model, you need to just train for a simple normal example. Like you need to just pass these values. Like you need to send the values for one example. If you are directly implementing this, so if I write directly tran.fit, it will give me an error. You need to run for one example initially because we are just implementing, we are inheriting this class. We need to run for one example so that the model will be seeing whether it is working or not. If you directly run that, it will throw an error. You can try around it. So initially I tried for one example. So here I have taken till -1. Why I have taken till -1? See, initially I have taken for one example, but I have taken till -1 as I already told you. We are taking size to be 13. And see, initially we have, let me show you English vocab size. English, okay, what is my English vocab size? English vocab size. So if I run this, I got 14,533. So this is what we get here, but we have +1 because we are also handling unknown tokens. So 14,533 number of outputs will be having in the output side. If you are willing to vice versa, this like if you want French vocab size here and English vocab size here, you'll be getting the size of French. Okay, this is about uh, now let us compile the model. So initially I'm taking sparse categorical cross entropy. What is sparse categorical cross entropy is, see, initially our input is in sequences like 12, 13, 14. It's not like 12 is not represented in one hot like 0000 followed by 1 at 12 and so on. So why we are not implementing this? Because this consumes more space, and whenever you execute it in our limited notebooks, you'll get graph execution error because our training examples is in lakhs. So if you are converting all this stuff into one hot, it will take a lot of time. So what we are doing is just simply do sparse categorical cross entropy. Okay, and we are taking Adam optimizer with learning rate as 1e minus 3, and we are taking the metrics as accuracy, and we have run this model, we have fit this model. So initially I trained for 2 epochs with batch size 512. So if I train this now, it will take a lot of time. See, it takes 315 seconds for one epoch. It's almost 5 minutes. So for 2 epochs it took 10 minutes for me. So I got accuracy as 77.97 for the first epoch and 80.99 for the second epoch. So now it's time for testing. So if you want to test the data, you need to pre-process the data. So I want to test the data. So initially I'm pre-processing the data. Okay. So I have created this function. I need to pair the function. I need to return the output. So I'm taking the English tokenizer as English tokenizer. I'm converting it into sequences. Then I'm writing a function which is called pred. So what does this pred do? It initially takes our input, which is I. So what is I actually? We are just we are testing from the training set itself. So if I is 10, we are just considering the 10th example of our training data. And what we are doing, we are taking the maximum value from our predicted model. Like we are doing tran.predict. We are taking the first ith example, then we are predicting it, and we are taking the 0th output, and we are concatenating it to our sentence. Then in the range of 12, why we are taking 12? Because our output size is 13. So initially we got start of sentence token, and we need to iterate it for 12 number of times. So we are taking it in the range of 12. We are implementing the same thing. We are taking the argmax. We are taking the maximum value of the predicted. We are storing it in word. We are adding this to sentence, and we are iterating it. This continues, and whenever our word is end of sentence, we have reached the end of sentence, we need to break it. So I have written the code for break, and we are returning the sentence. Let me execute this. Okay, let me just show you this thing. See, initially I'm taking 900th example. So you are really in bad shape. This was my French translation. Sorry, this is my input sentence, and this was my English translation. So what I have taken, I'm randomly taking training examples. So I'm importing random, and I'm writing this function. Initially I'm taking a random integer in this range. I'm converting this pre-process French sentences to using tokenizer. Then I'm predicting the sentence. I'm then converting the actual sentence. So ith example, this was let me show you. So French tokenizer dot this one. Let me copy this and paste it. Suppose I want 900th example, which I have shown already. Incomplete input. Sorry. So I got this sentence, right? And the actual output for this is let me copy this. So I is 900 here. So this is the actual output. So I have written the same thing here. This is the French sentence. This is the true sentences, and this is the predicted one. I have created the function, and I'm iterating it over 5 times. I want to check for 5 examples. So I've taken for I in range 5. See, this is the French sentence which I have sent, and this is the predicted and true sentence. See here, can open the whole time. A war may break out at any moment. No one knows very much. No one really knows. That's my brother is not, it's my father. So we have just trained for two epochs. That's why we got this kind of results. But if you train for 30 to 40 epochs, you'll be getting better results. And you can also play with this. Like if you change the number of dense layers, like you can change it to 1024 or any other stuff, and you can change the head nums. So based on your hyperparameters, the output of the model will be affected. So let me run this again. What happened? I guess. Okay. See, this was my output. Rigid fell. Pearl surgery. Try somebody. C. So why I'm getting these random values because our training data. I mean, we haven't trained the model perfectly. We are just trained for few number of epochs. That's why we got these kind of results. See, I would like to go for a couple of us. I would like to call on you one of these days. So your output will depend on number of epochs as well as the model and all the hyperparameters. So this way we are converting French sentence to English sentence. The only thing, if you want to convert from English to French sentence, you need to change here. You need to reverse these and you need to reverse the parameters. That's it. If you want to convert it into any language, just follow this code. You'll be able to achieve this. So this is the implementation from scratch. In the next video, we'll be discussing how to implement using other libraries. That's it for this video. Thank you.